Hello everyone and welcome to my lecture on factors affecting nucleophilic substitution reaction. Here we are going to focus on SN1 and SN2 reaction. Let's have a quick recap of SN1 and SN2 mechanism. SN1 reaction is a two-step process. The first step is the slowest step, leading to the formation of carbocation intermediate, and the second step involves attack of the nucleophile on the carbocationic intermediate to give the product. Let's have a quick look at the energy profile diagram of SN1 reaction. Y-axis represents free energy and x-axis represents progress of reaction. Starting material is converted to intermediate via the formation of transition state 1, and the intermediate is converted into product via the transition state 2. Since the energy barrier for the first step is high and therefore it is the slowest step. The carbocation intermediate formed during the reaction is planar and the central carbon atom is sp2 hybridized. The attack of the nucleophile can take place either from the top or from the bottom, leading to racemization of product in optically active alkyl halides. Therefore, the moment we talk about SN1 reaction, these are the important characteristics that comes to our mind. It is a two-step process. It goes through the formation of carbocation intermediate. There are two transition states. It is a first order reaction where the rate of the reaction is dependent only on the substrate concentration. If we start with an optically active substrate, we get a racemic mixture. Lastly, the rate of the reaction is of the order tertiary greater than secondary greater than primary halides. Now coming to SN2 reaction, it is a one-step process and the reaction proceeds through the formation of transition state where neither the bond between the nucleophile and the central carbon atom is formed completely, nor the bond between the leaving group and the central carbon atom is broken completely. This is the energy profile diagram of SN2 reaction, which clearly shows that the reaction goes through a single transition state. The transition states are highly unstable and cannot be isolated like intermediates. Intermediates can be detected and isolated. Higher the energy of activation, slower will be the rate of the reaction. Now in SN2 reaction, we do not get a racemic mixture. What do we observe then? We observe an inversion of configuration if the starting material is an optically active halide. Why do you think so? Let's see the mechanism again. OH minus, that is the nucleophile, attacks from the side opposite to the side from which the leaving group Br minus is leaving, and therefore the configuration of the product is exactly opposite to that of the starting material. If we start with an R isomer, the product is S and vice versa. So when we talk about SN2 reaction, these are the points that quickly come across our mind. It is a one-step process, proceeds through the formation of transition state and not intermediate. It is a second order reaction where the rate of the reaction is dependent both on the concentration of the substrate and nucleophile. SN2 reaction leads to inversion of configuration. Lastly, the rate of reaction is of the order primary greater than secondary greater than tertiary halides. There are 5 factors which affects the substitution reactions. They are nature of substrates, nature of solvents, strength of nucleophile, nature of leaving group, and concentration of the base. Today in this lecture we are going to focus on nature of the substrate. In the following lectures we will study other factors. Now, what do you mean by substrate? Substrate are starting material on which the actual reaction takes place to give the product. We are discussing about nucleophilic substitution reaction, and here we will see how the nature of the substrate governs the mechanism of the reaction, that is SN1 pathway or SN2 pathway. We'll do this portion through several examples. Example 1. The first compound is methyl bromide, second compound is ethyl bromide, third compound is 2-bromopropane, and fourth compound is 2-bromo-2-methyl propane. Now guess the rate of hydrolysis of these halides with base. It is observed that compound 1 and compound 4 undergo rapid hydrolysis and compound 2 and 3 are resistant to hydrolysis and the reaction is slow. Can you justify this? Where from you should start thinking? First, look at the nature of the compound. Is there any difference? If there is a difference, then in the second step, think what change it can bring in the mechanistic pathway. And in the third step, think about the electronic and steric factors operating in the molecule. Let's start then. Methyl bromide is a very good substrate to undergo hydrolysis via SN2 attack. Ethyl bromide is a primary halide, like methyl bromide. Ethyl bromide is also a primary halide and undergo reaction also via SN2 attack. 2-bromo-2-methyl propane, that is compound 4, is a very good substrate to undergo hydrolysis via SN1 mechanism as it is a tertiary halide. Compound 3, 2-bromopropane, can undergo hydrolysis both by SN1 and SN2 mechanism, and the rate of reaction is minimum in this case. Now let's have a look at steric and electronic factors operating in this molecule. First, inductive effect. It is observed that positive inductive effect disfavors SN2 reaction and favors SN1 reaction. Why? You have seen that in SN1 mechanism, the nucleophile has to attack the partially positive central carbon atom from back. More positive the central carbon, better is the attack by nucleophile. Now, as we go from compound 1 to 4, compound 1 has no methyl substituent. Compound 2 has 1, compound 3, 2, and compound 4, 3. We know methyl group has plus I inductive effect. That means it can donate bonding electrons and it can make the central carbon atom less positively polarized. Therefore, more number of methyl group means SN2 attack is disfavored, or in other words, positive inductive effect disfavor SN2 attack. Now let's have a look at SN1 attack. In SN1 mechanism, there is a formation of carbocation. So, more number of methyl groups, more is the plus I inductive effect, and more is the stability of the carbocation. And SN1 reaction is favored. That is why compound 4 undergoes substitution reaction via SN1 mechanism. Now let's have a look at the steric effect. Here I will give you an example. Supposing you are a nucleophile and you want to meet a friend which is supposed to be the central carbon atom in a crowded train. Do you think it is an easy job? Definitely not. But if the train would be less crowded, say on public holidays or on Sundays, you can easily approach your friend, right? Same thing happens in a molecule. More larger groups around the central carbon, more difficult for the nucleophile to approach central carbon atom, and so steric effect disfavor SN2 attack. This is the first reason. Second reason is in SN2 attack, the transition state has 5 groups around the central carbon. So more steric hindrance compared to the starting halide which had 4 groups around the central carbon. This again disfavors SN2 attack. But steric crowding favors SN1 attack. Why is it so? In SN1 attack, the steric crowding is relieved on going from starting halide to carbocation intermediate, as the intermediate has 3 groups placed far apart around the positively charged carbon center. Therefore, steric crowding favors SN1 attack. Next is hyperconjugation effect. Hyperconjugation effect favors SN1 reaction as it stabilizes the carbocation. All of you, do you know what is hyperconjugation effect? Hyperconjugation effect occurs in compound having CH bond alpha to the carbocation or double bond. What happens is the alpha CH bond breaks and donates its electron to the carbocationic center, which stabilizes the carbocation, and the H plus ion do not go far off but remains in the vicinity of the molecule. So, as many number of alpha CH bond, that many number of resonance structure possible in the molecule. More number of resonance structure, more is the stability in the molecule. So, as we can see, carbocation derived from compound 4 has 9 alpha CH bonds, and this compound will observe maximum hyperconjugation effect. Here I want to say some more things. How will you know that the alpha CH bond breaks during hyperconjugation? This we can know by secondary kinetic isotope effect. What is that? It is observed that if the alpha CH bond is replaced with alpha CD bond in original halide, where D stands for deuterium, the rate of formation of the carbocation is slowed down by approximately 10% per deuterium atom incorporated. This shows that CD bond was involved in the ionization process. Therefore, lastly we can say that plus I inductive effect, steric effect and hyperconjugation effect all favors SN1 attack. Let's move to the second example. Guess the rate of hydrolysis of this halide with water. Will the reaction go through SN1 or SN2 attack? To get the answer to these questions, we should follow the following steps. Step 1. Look at these compounds. What type of compounds are they? They are benzyl halides. Step 2. Think about the change it can bring in the mechanistic pathway. Step 3. Also think about electronic and steric environment. Now, whenever a phenyl ring is present in the molecule, we should think whether resonance stabilization by the pi electrons of the phenyl ring are involved in any step of the reaction or not. Let's see the answer. The pi electron clouds on the benzene ring will prevent the nucleophile to approach the carbon center from back. Therefore, less probability of SN2 attack in these cases. Here the reaction will go via SN1 pathway, as the carbocation intermediate can be stabilized by resonance with the phenyl ring. More the number of phenyl ring, more the delocalization of the positive charge, and more is the stability of the carbocation intermediate. So, the rate of the reaction increases from compound 1 to compound 3. Same is the case for allyl halides. Allylic cation can also be stabilized by resonance, and hence allyl chlorides are more reactive than alkyl chloride. Example 3. Do vinyl chloride and halogenobenzene normally undergo substitution reaction? The answer is no. But why? Notice in these compounds, though phenyl ring or double bond is present, resonance stabilization has no role to play. In this compound, the halide group is attached to a sp2 hybridized carbon atom, which is more electronegative than sp3 hybridized carbon, and will pull the halide group more towards itself, and the CCl bond becomes more stronger and it is difficult to break. So, no SN1 attack. Secondly, CCl bond is less polar because of less difference in electronegativity between the carbon and the Cl group. So, nucleophile finds it difficult to attack the carbon center from back. Moreover, the pi electron cloud prevents the nucleophile to approach the carbon center. Therefore, less probability for SN2 attack also. Hence, vinyl chloride and halogenobenzene are unreactive towards nucleophilic substitution reaction. Halogenobenzene undergoes SN2 type of reaction under special condition. Look at this example. Chlorobenzene do not undergo nucleophilic substitution reaction, but para-chloronitrobenzene undergo nucleophilic substitution reaction because of the activation of the ring by electron withdrawing group, that is the nitro group. Now let's move to example 4. It is observed that the reaction rate decreases along the series when the reaction is carried out in ethanol at 55 degree centigrade. How will you explain this? Step 1. Find the difference between example 4 and example 1. In example 1, the substitutions are on alpha carbon atom, and in example 4 the substitutions are on beta carbon atom. Step 2. Think, because of the change in substituent position, is there any change happening in the molecule that will affect the reaction mechanism? In this example, since substituents are at the beta carbon, therefore inductive effect do not play a major role and hyperconjugation is not possible. Here the steric effect plays the major role and the reaction proceeds through SN2 mechanism and not via SN1 mechanism. Step 3. Think how steric effect controls the rate of the reaction. As we move along the series, substitution increases at the beta carbon. This makes the approach of the nucleophile to the central carbon difficult and the SN2 reaction rate decreases. Step 4. But why do you think there is a large difference in the reaction rate of 1-bromo-2-methyl propane, whose reaction rate is of the order of 10 to the power minus 2, and 1-bromo-2,2-dimethyl propane, whose reaction rate is of the order of 10 to the power minus 6? Look at the figure below. Since the reaction proceeds via SN2 mechanism, there will be formation of transition state. In 1-bromo-2-methyl propane, the compound will have at least one conformer where the nucleophile, that is ETO-, will face less steric hindrance in transition state. But for 1-bromo-2,2-dimethyl propane, this is not at all possible. Hence, the rate of the reaction decreases drastically. Lastly, let's look at the effect of substituent at the bridgehead position. First, let us see what are bridgehead position. It is the position which is a part of two or more rings, or which is common in two or more rings in polycyclic molecules. Now, if you look at compound 1 and 2, they are tertiary halides, and therefore they undergo reaction via SN1 attack. As we have seen earlier in compound 1, SN1 attack is favored because of inductive effect, steric effect and hyperconjugation, And in compound 2, SN1 attack is favored because of inductive effect, steric effect and resonance. But why do the reaction rate decreases as we go from compound 3 to 4 to 5? If we carefully notice, they are also tertiary halides, and the halide is situated at the bridgehead carbon. If the reaction proceeds via SN1 mechanism, then there will be a formation of carbocation at the bridgehead carbon, which is very difficult because of the rigid molecular framework which prevents the carbocation to be planar. Therefore, the energy of the carbocation intermediate increases and the reaction rate decreases drastically. Compound 4 has a lower reaction rate than compound 3, shows that rigidity at the bridgehead carbon having one carbon bridge is greater than the rigidity at the bridgehead having two carbon bridge. It is observed that compound 5 has further more rigidity, and so the nucleophilic substitution reaction in compound 4 is almost not possible. Here we come to the end of the lecture. In summary, SN1 reaction is a two-step process, proceeds through the formation of planar carbocation intermediate. The rate of the reaction is dependent on the concentration of the substrate. The rate of reaction is of the order tertiary greater than secondary greater than primary. SN1 reaction leads to racemization in optically active substrate. Coming to SN2 reaction, SN2 reaction is a one-step process, proceeds through the formation of transition state. The rate of reaction is dependent on the concentration of substrate as well as on the concentration of the nucleophile. The rate of the reaction is primary greater than secondary greater than tertiary halides. SN2 reaction leads to inversion of configuration in optically active substrate. There are several factors which affects the nucleophilic substitution reaction. The most important factors are nature of the substrate, nature of the solvent, strength of the nucleophile, nature of the leaving group, and concentration of the base. Today we have seen how nature of the substrate affects the substitution reaction through various examples. And we have seen that inductive effect, steric effect and hyperconjugation, all these factors favor SN2 attack. Further, we have seen that larger the number of benzene ring, more is the delocalization of the positive charge and more is the stability of the carbocationic intermediate and more is the rate of the SN1 reaction. In benzylic cation and allylic cation, both the cations can be stabilized by resonance and hence the allylic halide like benzylic halides can undergo substitution reaction faster than alkyl halides. But we have seen that vinyl chloride and halogenobenzene are unreactive towards nucleophilic substitution reaction. We have also seen that as substitution on the beta carbon increases, it becomes difficult for the nucleophile to attack the carbon center attached to the halide from back, and therefore the reaction rate decreases. If the halide group is situated at the bridgehead of the bicyclic system, the system becomes very reluctant to undergo nucleophilic substitution reaction because of the rigid framework. That's all for today's lecture. Myself, Dr. Kakali Lahiri, signing off, and will be back soon in the next lecture. If you like my lecture, please subscribe and comment. The links for the earlier lectures are provided in the description box. Thank you and bye-bye.